In this video, we will introduce the concept of generative modeling. To understand what is meant by generative modeling, we will look first at generative design. If we look at the Wikipedia definition, it highlights a few key points. The most basic point is that it uses a program to generate outcomes. As we have already seen in the previous course, this program can consist of a set of procedures that generate 3D design models. The Wikipedia definition highlights two other key points. First, the overall process is iterative. This means that the process is typically used to explore many alternative design options. In the diagram, the iterative process is depicted as two nested loops, the ideation loop and the exploration loop. In the ideation loop, new concepts are created, while in the exploration loop, those concepts are developed, evaluated, and modified. It is in the exploration loop that computational approaches can be most readily applied. The second key point in the Wikipedia definition is that the outcomes that get generated may need to meet certain constraints. These constraints can make the coding of the program more complex. In this course, our focus will not be on generative design. Instead, it will be on generative modeling. The distinction between generative modeling and other types of parametric modeling is generally quite ambiguous and blurred. Both parametric modeling and generative modeling use a program with parameters to generate outcomes. In our case, we make the distinction based on the relationship between parameters and outcomes. With parametric modeling, the relationship between parameters and outcome is defined as being relatively direct. This means that it should be possible to roughly predict how a change to an input parameter would affect the outcome. For generative modeling, this no longer holds true. The relationship between the input parameters and the outcomes becomes more complex. This increase in complexity is influenced by two factors: rule-based modeling and constraint-based modeling. We will look at an example of each of these next. With rules-based modeling, a set of simple rules are defined in the code of your program. These rules can then be applied multiple times to generate the final outcome. When multiple rules are used, rule application can get complex. In some cases, the rules can also be recursive, which means that the rule can be applied to its own output. The example shown here is a simple recursive rule that divides a polygon into two polygons. The rule is repeatedly applied until the lengths of all the polygon edges are less than a specified maximum length. Here is a more complex example of a recursive rule. The form is generated by repeatedly extruding one side of a box to generate another box. The rule is specified as a sequence of numbers, where each number represents the side of the box to extrude. The three sequences of rules that generate the three forms are shown. These rules can be specified as input parameters, so that varying the rule will vary the form. However, given a particular rule, it is difficult to predict what the outcome will be. In such a case, the process would likely be more of a trial and error exploration. With constraint-based modeling, the models that get generated all need to adhere to certain constraints. These constraints can be provided as parameters, or can be hard-coded in the program. The process of satisfying constraints can vary, with many different types of approaches and techniques being possible. In some cases, constraint satisfaction can require dynamic form-finding techniques. In other cases, the constraint may be solved analytically. We will look at an example of generating urban blocks, where the plot ratio is constrained. The program generates a set of buildings with randomized varying heights on an urban block. Based on the plot ratio, the total combined area of all the buildings is required to be approximately 80,000 meters squared. In this case, the program adjusts the heights in a randomized way, while at the same time ensuring that the total floor area remains close to the target. This means that when one building gets taller, the other buildings need to get shorter. Next, we will look at 2 more examples of programs that use rules and constraints. In this first example, the program generates plans for an urban district. A series of urban nodes and sub-nodes are specified. Roads are then generated connecting the nodes and other neighboring roads. Blocks are then divided into plots which need to adhere to the area size and shape constraints. Finally, building typologies are inserted that vary based on proximity to the nodes. Looking in more detail at a smaller area, a program can generate alternative massing options. Each option can be populated with different building typologies. However, the program will ensure that each option will have the same total floor area. Additional metrics can be then calculated as a basis for further comparison. In this second example, the program generates a high-rise residential development. The development consists of a cluster of high-rise buildings with apartments. The total number of buildings can vary, and each building has a mix of apartment types. The program generates alternative design options. Each option has different numbers of building with differing heights and configurations. However, the total floor area and the total number of apartments for each type remain constant.